Hello everyone, welcome to this lecture titled Organized Sound Spaces with Machine Learning. We will be looking into how we can use a few different machine learning approaches to create abstract sound spaces that are organized in a way where similar sounds are brought together closer to each other. My name is Kıvanç Tatar. I am an assistant professor in interactive AI at Data Science and AI Division at Computer Science and Engineering Department at Chalmers University of Technology. I am tuning in today from Göteborg, Sweden. I am also a WASP HS Fellow, which is a program looking into researching AI and its applications with perspectives from interdisciplinary approaches, including social sciences, human-computer interaction, artistic practices, and etc. The works that I'm gonna be showcasing today are some of them are my works, and they have been funded by quite a few different funding agencies historically as well. Before diving into machine learning approaches, it is good to talk about materiality of music and give a background in what we mean by music and what kind of music that we are interested in this lecture. First, I want to talk about expansion of musical material and looking into the beginning of 20th century and advancements in futurism and more. And then I want to look into the mid 20th century where we start describing music as organized sound. Let's start with expansion of musical material. Let's go back to the beginning of 20th century and try to understand, try to imagine what music meant back then. For example, this piece by Richard Strauss is composed in 1915, and this is a recent performance of that symphony by Oslo Philharmonic, which was performed in 2019. In the beginning of 20th century, we had a quite concrete understanding of what music is and what kind of sounds were musical. We had an understanding of what kind of instruments, musical instruments, that we could use to make musical sounds. Of course, some composers were disagreeing with that, such as Luigi Russolo. Around the same time in 1913, Luigi Russolo released his Futurist Manifesto. It is a very interesting time to do that because at that time our cities have changed. They are quite loud. We have been in industrial revolution for quite a while at that time. So you could imagine that the soundscape of our daily lives in the beginning of 20th century were quite noisy. And I would like to read this paragraph from Luigi Russolo's Futurist Manifesto. Luigi Russolo says, "Let us cross a large modern capital with our ears more sensitive than our eyes. We will delight in distinguishing the eddying of water, of air, or gas in metal pipes, the muttering of motors that breathe and pulse with an indisputable animality, the throbbing of valves, the bustle of pistons, the shrieks of mechanical saws, the starting of trams on the tracks, the cracking whips, the flapping of awnings and flags. We will amuse ourselves by orchestrating together in our imagination the din of rolling shop shutters, the varied hub of train stations, ironworks, treadmills, printing presses, electrical plants, and subways. And Luigi Russolo suggests musicians that futurist musicians should substitute for the limited variety of timbres that the orchestra possesses today the infinite variety of timbres and noises reproduces with appropriate mechanisms. Let's listen to an example from Luigi Russolo's futurist intonarumori. These are devices that are made to make noises. You could call them noise instruments. And they have been proposed in the beginning of 20th century as a way of expanding our sound palette for musical practices. Quite noisy. This was the expansion of our musical material. Later, towards the mid-20th century, some composers started to think about what is then to make music if we can use any sound as musical material. One of those composers was Edgar Varèse. And again, I would like to read a paragraph from an article titled Liberation of Sound by Edgar Varèse. First of all, I should like you to consider what I believe is the best definition of music, because it is all-inclusive, the corporealization of the intelligence that is in sound, as proposed by Vronsky. If you think about it, you will realize that, unlike most dictionary definitions, which make use of such subjective terms as beauty, feelings, etc., it covers all music, Eastern or Western, past or present, including the music of our new electronic medium. Although this new music is being gradually accepted, there are still people who, while admitting that it is interesting, say, but is it music? It's a question I am only too familiar with. Until quite recently, I used to hear it so often in regard to my own works that as far back as the 20s, I decided to call my music organized sound, and myself not a musician, but a worker in rhythms, frequencies, and intensities. Indeed, to stubbornly conditioned ears, anything new in music has always been called noise. But after all, what is music but organized noises? And a composer, like all artists, is an organizer of disparate elements. So, Varèse opens up the idea of music, starting from the expansion of musical material and thinking about how can we call something music if we think that any sound can be musical. And in his definition, it is the organization that matters. And following Varèse's suggestion, we also have other composers coming in and giving us a little bit more understanding of the materiality of music. So we started from Luigi Russolo's expansion of musical material, and then we came to Varèse's understanding of music, a generalized definition of music, and then after that, Karl-Heinz Stockhausen proposes 4 criteria of electronic music, and then later in the 20th century he also expands those criteria and adds more criteria to his definition. But in this beginning he starts with 4 of them, and then without getting into the details of those criteria, he emphasizes the relationships between pitch, noise, timbre, rhythm, and how music consists of multiple musical layers. And then also Stockhausen emphasizes the 3D, physical 3D space that we can use for musical composition. And in the beginning of 21st century, Curtis Rhodes proposes the time scales of music in multiple levels. Without getting too much into the details of materiality of music, let's see an example in which a composer, Delia Derbyshire, is using any sounds, processing them, and making a composition out of those organizations. And in this video, Delia Derbyshire explains what kind of musical materials she used to compose the theme of Doctor Who.
Stage in the realization of a piece of music is to construct the individual sounds that we're going to use. To do this, we can, if we like, go to these sound generators here, electronic generators, and we'll listen to 3 of the basic electronic sounds. First, there's the simplest sound of all, which is a sine wave. As you see on the oscilloscope, it has a very simple form and has a very pure sound. Now we listen to the same note, but with a different quality. This is a square wave. You see, it's very square on the picture, and it's perhaps rather harsh to listen to. This is because it has a lot of high harmonics, and that's what gives the corners on the picture. A more complex sound still is white noise. But those basic sounds aren't really interesting in their raw state like this. To make them of value for a musical piece, we have to shape them and mold them. But using all of these, we can build up any sound we can possibly imagine almost. We spend quite a lot of time trying to invent new sounds, sounds that don't exist already, sounds that can't be produced by musical instruments. But we don't always go to electronic sound generators for our basic sources of sound. If the sound we want exists already in real life, say, we can go and record it. The sound I want for the rhythm of this piece needs to be a very short, dry, hollow wooden sound I can get from this. And then the sound for the punctuating chords, I want the sound of a short wire string being plucked. That's at the speed we recorded in the studio. We can get the lower sounds we need from the rhythm by slowing down the tape. And the higher sounds by speeding up the tape. These particular pitches we can record on this machine here. And then all we have to do is cut the notes to the right length. We can join them together on a loop and listen to them.
In that video, Delia Derbyshire showed us how she was selecting different kinds of audio and how they relate to each other. For example, how does a sinusoidal sound? How does a square wave sound? After selecting the musical material, let's see how Delia Derbyshire is composing the Doctor Who theme using that material.
And then all we have to do is cut the notes to the right length. We can join them together on a loop and listen to them. And then with the higher notes of the rhythm, again we join them together on a loop and play it in synchronization with the first tape. over this we can play the sound of the plucked string, which can be either in the form of a loop like this, that's in synchronization, or in the form of a bend on a tape.
This documentary from BBC is a great example to see how a composer works with both audio spaces organized in a way that we have an understanding of audio similarity and audio dissimilarity. It also showcased how we organize sounds in time so that we come up with musical form, whether it is performance or composition. We can map both of those musical applications to machine learning approaches. For example, to organize sounds in an abstract space of similarity and dissimilarity, we can use this notion of latent space in machine learning and use various machine learning approaches to create those latent spaces. On the other hand, to organize sounds in time, we can use a variety of sequence modeling approaches or machine learning approaches for time series data. But what is a latent space? Let's have an example of that. For example, if we think about a latent space of colors, and if we define a color as 3 values of RGB, red, green, and blue, let's think about a way of organizing those colors on a 2D surface. And let's see an example of that. This algorithm is called self-organizing maps, which has a predefined number of nodes that moves itself so that it takes the shape of the latent space. And in our case, it takes the shape of the color space. Towards the end of the training, we can see a variety of colors and how they relate to each other, how they are similar or dissimilar to each other. And now we are here at latent audio spaces, the main topic of this lecture. Today we will be looking into 2 types of approaches to latent audio spaces: discrete approaches and continuous approaches. What is a discrete approach and what is a continuous approach then? There is actually no continuous approach. All of the approaches that I'm going to mention here are mathematically they are discrete approaches, but the continuous approach is working in the time scales of microscale, and the discrete approach is working in the time scale of sound object and mesoscale, in the sense that in discrete latent spaces we are organizing audio samples that are either fraction of a second to a couple of seconds in an abstract space. We can think those as sound objects, short sound gestures and such. In the continuous latent spaces, we are working in the micro scale. We are working with audio windows that are quite short, around 12 milliseconds, 11 milliseconds to 40 milliseconds and such. Thus, by putting one audio window after another, we treat it as a continuous latent space. We will get to the details of that in a second. Again, discrete latent audio spaces work with meso and sounds object timescales, whereas continuous latent audio spaces work in microscale. Let's start with discrete latent audio spaces. To create a discrete latent audio space, we need to do 2 things. We need to first find a way to represent an audio sample, and then apply a machine learning approach to generate a latent space. We need to find a way to represent audio sample because we cannot just work with audio as a signal in these approaches. And in some applications, we will see that the duration of the audio is also different, and we need to come up with a series of numbers, and the number of numbers in that series of numbers has to be the same across all audio samples. So what we are going to do is we are going to do what we call a feature extraction. And there are a variety of ways to extract features from an audio signal. For example, we could extract spectral features. There are quite a different types of spectral features, but in two categories we can cluster them. The first category is Fourier transform based approaches, in which we have the audio window static across different frequency bands, and there are wavelet based transforms such as constant Q transform, in which we have the audio window changing across different frequency bands. For example, for lower frequency bands we have a longer audio window, and for higher frequency bands we have a shorter audio window. So we could use spectral features and calculate the spectrogram of an audio signal so that we could train a machine learning algorithm on it. Or we could also use higher level features. For example, on the right here, we see a representation of audio samples from Stockhausen's composition titled Contact. Here in this image on the right, each segment is labeled on a two-dimensional effect estimation model. In this effect estimation model, we have arousal and valence. Arousal refers to the eventfulness of sound, whether it is calm or it is quite eventful. Valence refers to the pleasantness of sound, whether it is sort of sad or something that initiates negative emotions versus something that could initiate positive emotions. We have publications on this, if you're interested, showing that there has been consistency across a variety of people rating these. And on those ratings, we trained the machine learning algorithm to come up with this. But here what I'm trying to say is that we can have also higher level features and train a machine learning algorithm on those features as well. Let's see an example in which we calculate higher level features on a data set of audio samples. We will first start by a chaotic sound. Low arousal calm sound. More pleasant sound. A little bit more eventful and pleasant. Another chaotic. A calm sound again. Those higher level features was part of a system that I created titled Musical Agents Based on Self-Organizing Maps. And there's quite a lot happening in this architecture. Without going into too much details, I would like to give a brief overview of how it works. Here on the image on the right, in section A, we have an audio waveform, which is processed through a audio segmentation algorithm, and we find automatically different audio segments. To generate a data set of audio samples in which we have audio samples that are either a fraction of a second or a couple of seconds. Using that audio data set, we extract a set of features from that, and then we train a sound memory. And then this is this sound memory is a discrete latent audio space. It is the same architecture that I just showed as an example to organize colors on 2D domain. Using that sound memory, we go back to the original recording and we label each audio sample with their corresponding clusters in the sounding memory, which gives us a symbolic representation of our composition. And at this point, it's really interesting because this recording is, by the way, one of short compositions of Xenakis. And it's very interesting that even in this short composition, this approach has found patterns. For example, the composition starts with 885, and then we see 885 again somewhere in the middle of the composition. Looking at such symbolic representation, we can use sequence modeling algorithms in machine learning to try to find recurring patterns in that symbolic representation. We could use this approach to perform music with it. We could apply a discrete latent audio space generated by the self-organizing map approach and combine that with a sequence modeling algorithm such as factor oracle or recurrent neural networks to come up with a system that reacts to other performers in real time. Here in this image, what we see is we have a performer who is creating an audio output in real time, and this performer's output is fed into the system. The system first carries out a feature extraction, try to understand where the performer's current state is in the self-organizing maps, in this abstract, discrete, latent audio space. And it keeps a track of that, and it tries to match what happened with the patterns that it has in its memory. Patterns such as 885, as we just saw here. For example, maybe the current state is cluster 8, and then the machine knows that after cluster 8, there are two other clusters that it could play, 8 again, or the cluster 5. And choosing sounds, deciding on which cluster to play and then choosing sounds from that cluster gives us the audio output and the reaction or the performance from the machine learning system. Let's see an example of this. In this example, which is a work titled Conversation with Artificial Intelligence that I have made and recorded in 2017, we will hear the machine output in one channel, and we will hear the human performer, my output, on the other channel. The video will start with the machine output, and you can tell the first channel that you will hear is the machine's output. Let's hear 1 minute from this work. In that example, we had a feature extraction in which we were calculating 35 dimensions, 35 numbers on an audio sample. And those numbers consisted of timbre features, loudness, the duration of the audio segment, and musical motion recognition features. In regards to timbre features and loudness, we were calculating the statistics on those features because we have a varying duration in audio samples. So what we do is per feature, let's say loudness, we calculate a mean and standard deviation of the loudness across whole audio sample, which gives us two values to be added to the feature vector. And that feature vector is how we describe or define the audio sample to train a machine learning model on it. Let's see another example in which we have a relatively small self-organizing maps, and there we have clustered audio samples, and we can see how that clustering worked by listening to the audio samples within clusters. This example is called Audio Stellar. In a similar way, the authors here organize sounds in a 2D space, and each dot here will represent an audio sample. They are using a different feature extraction and a different clustering approach, but at the end of the day, it's a very similar pipeline. Let's see what it is. One exciting aspect of Audio Stellar is the user interaction possibilities that is already available in it. You can create these paths or generative ways to use the latent space, to use the discrete latent audio space in a musically meaningful way. Let's have a look at the machine learning pipeline behind Audio Stellar. We have a dataset of audio files which are going through a feature extraction process, which the authors call pre-process. So all audio is converted to a monofile, and then they are calculating a spectrogram feature called short time Fourier transform, so that they end up with a matrix that represents the audio in a different way. From that spectrogram representation, they first run their first machine learning algorithm, which is called principal component analysis. Using principal component analysis, we can keep the main features or the main distribution in the original dataset while representing it in a lower dimensional domain, such as in 3 dimensions or 2 dimensions. After that, the authors use a stochastic visualization technique, which is called TSNE, T stochastic neighboring embedding, to come up with a visualization of the dataset in 2D domain in which we can see clusters appearing. We still don't have the clusters to actually come up with the exact borders of those clusters. They are again applying a machine learning approach called DB scan. And after this pipeline, we have a 2D discrete latent audio space in which we can see clusters, which are represented as colors, in which we have circles, which are audio samples. And we can play with that in a musically meaningful way. Until now, we have covered 2 examples of discrete latent audio spaces. Now, let's have a look at continuous latent audio spaces. What do we mean by continuous latent audio space? As I mentioned earlier in timescales of music, when we talk about continuous latent audio spaces, it is actually not mathematically continuous. It is still discrete, but the discrete elements that we have are so short that we can approach them as if they are infinitely small or they are audio quanta. For example, here we have a frequency sweep that is starting from 220 hertz going up to 1000 hertz. And here we can see that sweep almost as if it is a path, right? The question here is, can we come up with a more complex way in which we have 2D representation of an audio space, and in that 2D representation we can see an audio file almost like a path? Because there are quite interesting musical applications that we could explore using such approach. For example, here in this image we see 3 colors, red, green and blue, and in those 3 colors we see quite small circles. And what these colors represent, the red colored path and the blue colored path, they are recordings from an audio dataset. Each circle in those paths represent one audio window. This is really interesting because this is actually an emerging property of a machine learning approach that I will be talking about in a second. And in that way, here, what we have is actually not a continuous, mathematically continuous space. It is still discrete, but because each audio quanta or audio window is quite small, we could almost approach each audio sample as if it is a continuously changing representation. To understand how we could create a continuous latent audio space, we need to first talk about a specific type of machine learning algorithm titled variational autoencoders. Variational autoencoders are a type of deep learning architectures. Let's first talk about an autoencoder. What an autoencoder does is it creates a latent space using the dataset. And it does that by trying to generate a latent space and then trying to reconstruct the original data using that latent space. Here in this example, we see a portion of a latent space in which we organize handwritten digits. And we can see that by just looking at the pixels, the architecture could organize a latent space of handwritten digits in which we could do morphs from one number to another. There is a page on Towards Data Science that I really like, and I think it's a really great resource on variational autoencoders, which covers the topic in a very brief manner. The following slides will include images from this source. An autoencoder consists of two main parts: a neural network encoder and a neural network decoder. In terms of the layers and how layers are set up, the decoder is the mirror, in most cases, of the encoder. And in the middle, we have a bottleneck layer or the latent layer. Here in this image, on the left, X is our input data and X cap is our reconstructed data. Remember, this is an autoencoder, not a variational autoencoder. And the loss function here is a simple check between reconstruction and the original data. We are looking at the distance between the reconstructed data and the original data. What does an autoencoder do and how is it different? Remember, I mentioned another machine learning approach called principal component analysis. In principal component analysis, we are trying to come up with a lower dimensional representation of the original dataset while keeping the main properties of that dataset. What do we mean by that? For example, on the left, let's look at a dataset that is in 3 dimensions. And maybe we want to use PCA to come up with a 2-dimensional representation of it. With a mathematical approach, we come up with a plane in which we still have relative distances, similarities and dissimilarities between data points while representing that data set in a 2D domain. Principal component analysis is great, but it has one feature that is not always preferred. And that is, in principal component analysis, the dimensions are orthogonal to each other. In autoencoders, though, we do not have to have dimensions orthogonal to each other. We could have arbitrary dimensions, which can be useful in certain applications. And let's say we have an autoencoder that looks at shapes and it tries to regenerate or reconstruct those shapes. What the autoencoder does is, first the input data is passing through the encoder and then it ends up at the latent space in the middle. And we organize those different shapes in that latent space. But we want to have this latent space because we want to also create new data points or new samples in between the data that we have in our training data set. This is not that possible using the simple autoencoder approach. Variational autoencoders address this by representing each data point as a Gaussian distribution in latent space. In comparison to autoencoders where we have the data points as single points in the latent space. When we represent data points as a Gaussian distribution, then we end up with these regions where the distributions are getting closer to each other so that we can generate a new sample in between the data that we have in the training data set. And this is quite exciting. One point to consider here is that we need to be mindful about our regularization term. If we have that regularization term quite weak because it has a multiplier, if we set that multiplier too low, then we will have our Gaussian distributions too far from each other and we will still end up with noise or meaningless data points. But if we set it too high, then these Gaussian distributions are going to be too close to each other and our decoder won't be able to differentiate a triangle from a circle. And this will make our reconstructions to deteriorate. So we want to set up a multiplier for that regularization term in which our Gaussian distributions are close enough to each other so that we could create data points in between them, but separate apart so that our reconstructions are still high fidelity. How do we do that? How does the architecture work? Our regularization term is KL divergence, which is a mathematical way of measuring distances between two probability distributions, such as Gaussian distributions. There's also another issue here that because Gaussian distribution is a stochastic method, it affects our backpropagation in deep learning. That is, we need to have our all deep learning pipeline differentiable to be able to have our loss improve during training. So, to be able to deal with that, we have the Gaussian distribution as a sampling function on the side. And in our pipeline, our encoder outputs the mean and the standard deviation for that Gaussian distribution. We sample a vector from that Gaussian distribution using the mean and standard deviation from the encoder. And using that generated vector, we use our decoder to reconstruct our original data input. This is how a variational autoencoder works. We can use variational autoencoders in musical applications as well. In this work, titled Latent Timbre Synthesis, we are training a variational autoencoder on a specific type of spectrogram representations called constant Q transform. Constant Q transform is a wavelength-based spectrogram in which the frequency bands have different audio window lengths. So in this pipeline, we have an input waveform at the top, and we calculate the CQT spectrogram from it. The CQT spectrogram is passed to a variational autoencoder. The autoencoder creates us a latent space of spectrograms, and then those latent vectors later can be passed to the decoder. And then decoder again creates spectrograms, single spectrogram vectors. Then we can apply a phase reconstruction algorithm because our variational autoencoder works in the magnitude domain. It is only working with real numbers. Thus, the CQT spectrograms doesn't have phase. So in this last step, we are taking the magnitude CQT spectrograms, running a phase reconstruction called Griffin-Lim algorithm on it to generate an audio signal. This is the user interface of latent timbre synthesis. We have two audio files, and using latent timbre synthesis and a continuous latent audio space, we can create interpolation curves that are changing in time. What this interpolation curve does or mean is that if we set it up closer to 1 or closer to the top, the generated output for that time point or that audio frame or that moment, it is going to be similar sounding to audio 1. It's going to be closer to audio 1. As we set the interpolation curve lower, at that particular time point or moment or at that audio frame or audio window, it is going to be more similar to the second audio. And the rest of the framework is about loading data sets and different runs in which you could have different machine learning models, and setting up our inputs and outputs and selecting different sounds and selecting different regions in those sounds to generate different interpolation curves in an interactive way, and sound designing with this whole approach. Let's see how we can use latent timbre synthesis in an interactive way for sound design applications. Here we will choose one sound, set our length, a second sound, draw an interpolation curve, and generate a new sound. Let's select another sound maybe. Here, on the left, what we see is a representation of the latent space that's generated by a variational autoencoder. The examples that we just heard was from this particular trained model. Here, what we see is using T stochastic neighboring embedding, TSNE, as an audio stellar, we visualized the latent space generated by the variational autoencoder. One emerging property here is that even though we didn't give any information to the machine learning algorithm that where or which audio sample the audio frame is coming from, we can clearly see here that there are certain paths or certain squiggles appearing. If we dive into some of those squiggles and zoom into them, on the right, we see again a red path and a blue path. In those, each circle is an audio frame from the original audio recording. And even though we didn't explicitly give this to the machine learning pipeline, an emerging property was that the audio frames coming from the same audio files are appearing now as a path in latent space. And thus, this is a continuous latent audio space. The green path that we see is an interesting one. If we take the latent vectors of each audio sample in blue path and the red path, and if we find the middle point in between them in their original higher number of dimensions, if I'm not mistaken here 64 dimensions, if we take the middle point in each audio in each latent vector of an audio frame, here we end up with a green path, and this green path is supposed to be the middle point in between those two audio samples. And using that region between red path and the blue path and creating a variety of green paths, as we saw in the previous example, we can do sound design. And this is how latent timbre synthesis work. To sum up, in the first part of this lecture, we covered the materiality of music. We dive into musical composition and sound studies in 20th and 21st century. First, we covered the expansion of musical material, starting from the beginning of 20th century with the Futurism movement. And then we talked about the new approaches to music as organized sound. To give you an introduction to materiality of music and to ground our latent audio space approaches in sound studies and musical practices. After that, we dived into two kinds of latent audio spaces. First, we dived into discrete latent audio spaces, in which we worked with audio samples ranging from a fraction of a second to a couple of seconds. Then we dived into continuous latent audio spaces, in which we used audio frames that are ranging in 10-12 milliseconds up to 50 milliseconds. Thank you so much for joining me in this lecture, and I'm happy to answer your questions if you have any, and feel free to contact me. Have a great day.